Okay, I'm recording. First thing I want to do today is solve the last problem from yesterday. And this has to do with something that was never built, but was started at least. And then I wanted to announce, and I'll put this up in print somewhere on the Canvas site, or just send out an announcement. Tomorrow, I'm not going to have a live recording. I'm going to either record a separate one tonight, or on my YouTube channel, I've got a lecture I recorded, not last year. Would have been a while back, but it's on the material for what will be tomorrow. And so I'll make that available. Okay. With that out of the way, I should put the chat up here so if you have a question, I can see it. This is another problem just having to do with moving charges in a magnetic field. And it's about the superconducting super collider, which was something that was planned and in the planning stages for years. And they'd started constructing it, and it was going to be a huge ring of radius 13.8 kilometers. So the diameter would be like 26 or 27.6 kilometers, which is huge. And it was under a plane in Texas near Waxahachie, Texas, wherever that happens to be. And they actually started the thing. And I think there may be a picture in your textbook of how large the tunnel was going to be just inside the tunnel, but it was this huge circular tunnel underground. And in 1994, well, actually, it was all politics planning where it was going to be built, and somehow the Texas congressional team was more powerful than the ones from any other state, and they managed to get it built in Texas, but they got part way and ended up canceling it. And so I don't know what they do in the part that they did. It wasn't anywhere near the complete circle that was built, but I don't know if they're growing mushrooms there now or what. But at any rate, they were going to have magnetic fields of magnitude 5 Tesla, which is pretty darn strong. But actually, that's about how strong they are in an NMR machine. Let's see, I think that's what they call them. No, they don't call it that anymore. I forgot what the new name. Originally, they called it nuclear magnetic resonance. And then, well, people didn't want that for a medical diagnostic technique, so they call it something else now, which doesn't come to mind right now, whatever it's called, but it doesn't have the word nuclear in it. So people are much more happy about it. And it's an expensive thing, but they're strong magnetic field. They've got one in, well, it's part of the Confluence Health, and they bring a truck over from Wenatchee periodically a few times a month and operate it in Moses Lake. And I had one of those medical diagnostic things, and I'd been in a car accident and had a couple of compression fractures in my back, and they looked at them with that. And anyway, didn't seem to hurt me any. And actually, it's just the stuff in your body that's resonating, but it's part of the nuclei and hydrogen atoms, I think. Anyway, what's the magnitude of the momentum of a proton that moves in this way? So a ring of that much, and that's the strength of the magnetic field. And we're going to be using this idea again that the force that's on the proton is going to be QV cross B. Well, we know what the magnitude of the magnetic field is. And we have to figure out just what's going to go on. let's see, for protons with this momentum, the energy is given to excellent accuracy by E is equal to P times C, where P is the momentum of the thing, and then C is the speed of light. So they're going to be going close to the speed of light. And we want to then calculate the energy of the proton in mega electron volts. So we'll be converting from joules to electron volts. So this is the force. This will give rise to an acceleration, and it's traveling in a ring of the radius that they gave us, 13.8 kilometers, which is crazy. And this will be mv squared over that radius, and its direction is always going to be inward on this thing. And so I don't know what to call that unit vector, but we could call it r hat, I guess. No harm in doing that, because we're going to convert to a scalar equation here right away. Now, for maximum efficiency on something like this, you would want the velocity perpendicular to the magnetic field. And so at any given moment, if the velocity is in this direction, you'd want a magnetic field that might be pointing down. In fact, V cross B for a proton, that would do it. Yeah, so you'd have that in there. So what we'll be after here is QVB is going to equal mv over r, mv squared over r. So there's a nice scalar equation now. We know Q, we know B, and if I divide both sides by V, I'll get Q times B is equal to mv over r. What is the magnitude of the momentum of a proton that moves in this way? Well, momentum is just mv. So although usually, well, we'll find out in our last unit this quarter when we study special relativity that we have to do something else when something's moving close to the speed of light. But for this, we'll ignore that. Anyway, the momentum would equal just QBR. And so let's see how this comes out to units of momentum, which should be kilogram meters per second. But let's see how that comes out of here. Okay, Q is going to be 1.60 times 10 to the minus 19th coulombs, because it's a proton. B is 5 Tesla. So we're not going to have a lot of significant figures, except I'm going to write that Tesla as a Newton per amp meter. And then I multiply by the radius of this thing, which is 13.8 times 10 to the third meters. Okay, so what's going to happen to the units here? Well, I'm going to have to take this Tesla and break it down some more. The Newton on top is a kilogram meter per second squared. And on the bottom, I have a coulomb per second. That's what an amp is, times a meter. So these meters divide out. And let's see, if I invert this and multiply, I'll have times seconds over coulombs, and this whole thing turns into a kilogram per second coulomb. Okay, that's the most fundamental way of actually writing a Tesla. I'm multiplying that by a coulomb, so the coulombs are going to go away, and I'll have kilogram meters per second, which is what I expect. So I just have to multiply that together, and I'll get the SI unit for momentum. Oops. Mm. Okay, doesn't look like much, but it's only a proton. 1.1 times 10 to the minus 14th kilogram meters per second. Okay, and then calculate the energy of the proton, the kinetic energy. It's just going to be PC, and then we'll convert that to mega electron volts. So the energy is going to equal, this is P, by the way, momentum. So we just take that, 1.1 times 10 to the minus 14th kilogram meters per second times 3 times 10 to the 8th meters per second. And you can do this in your head. Be about 3.3 times 10 to the minus 6 joules, I think. But and actually, we've only got one significant figure, so 3 times 10 to the minus 6 joules, because it'll be kilogram meter squared per second squared. So that's the energy. But now to convert that into the mega electron volts, 3 times 10 to the minus 6 joules times, well, let's see, 1 MeV over 1.6 times 10 to the minus 13th joules. So this is going to be a fair number of MeV, actually. Yeah. Well, let's just call it 2, because that's all the sig figs, times 10 to the 7th MeV. Now, let's see. I think the rest energy of a proton is 939 MeV. So this is way more than that. That's 20 million MeV. So this thing is going at very close to the speed of light, and we shouldn't be using non-relativistic expressions to figure this out, but it's early in the book and we don't have the means to solve those things. So maybe we could revisit this problem. Except we don't actually do that part of special relativity. I was thinking when we got to the special relativity unit, there's some interesting things that happen in some fields. And when I was in graduate school, the area I worked in was nuclear theory. And when we talked about the mass of a proton, it would be written as this, that the mass was equal to 939 MeV over C squared. Okay. Well, wait a second. Okay, this is an energy. We're dividing by C squared, and somehow that's supposed to be a mass. Well, if you multiply out from underneath by C squared, you get MC squared is equal to 939 MeV. So that's Einstein's famous equation, E equals MC squared. So this is like the rest energy of a proton, the energy that it has just by existing and having mass. And this lets you calculate what that mass happens to be. So odd systems of units sometimes. Okay, on to some new things. And actually, I'm going to first go to something that's pretty old, and that is we're not so old. It's something that when we studied electricity, we didn't really look at electric current in any detail. And let's imagine that this is a wire. We're just sort of looking at it. And we're going to imagine some little slice of this wire internally. And I'm going to consider an electric current that's flowing in this wire. And we'll imagine that the electric current is going in that direction. So this will be an electric current will actually be composed of electrons, and there will be an electric field that pushes the free electrons through the wire. Now, we want to kind of imagine that there's a whole bunch of electrons that are sort of free, but they just kind of stay put if you didn't have an electric field acting on them. But we'll imagine that the average electron speed is equal to v sub d, and this is stands for the drift velocity of the electrons under the influence of this electric field. So you apply an electric field. Actually, in this case, you'd have your electric field pointing in this direction, but the electrons go opposite the electric field. And so that's something that they do. And I'm going to imagine that this little length right here happens to be v sub d times dt. This is the region of space where in a time dt, all of the electrons in here will pass through this end of the little imaginary chunk of space that I've got here. Well, how many electrons are going to be in there? Well, I'd have to calculate the volume of this. And let's just suppose this has a wire that has a cross-sectional area of A. Then the volume that I've got there is going to be A times V sub D dt. And it's just the cross-sectional area times the length. So that's what the volume is. Oh, this is a capital V for volume. Okay. And how much free charge is going to be enclosed in there? Well, let's suppose we have N electrons per unit volume. And each of the electrons is going to have a charge Q, which is 1.60 times 10 to the minus 19th coulombs. And so the amount of charge that's in here that's going to flow through that thing, dq, will equal N times Q, number of charges per unit volume, times the volume that I've got there, which is A V sub D dt. Okay. Now, if I divide both sides by dt, I'll get dq dt, and that's current. So that's just going to equal NQ A V sub D. So that's what will comprise an electric current. Okay, now that's as much as we need to do to look at some problems, although sometimes people will study something called the let's see, the current density, and it's actually the current per unit area of the wire. And so you divide the A through there. Uh-oh, did we lose something? My computer just made a noise. I don't know why. We'll ignore that. I think we're still good. Are we still recording? Did I click record? I did. Good. Anyway, sometimes you'll talk about I over A, and that's current per unit area in the wire, and they use the letter J for that for some reason. And that would just be NQV sub D. But I don't know that we're going to need to do that. And this is a vector. They'll actually put an arrow on here and put an arrow on the drift velocity. So anyway, our new idea for today, and for a couple of examples, we're going to calculate the drift velocity. So a silver wire 2.6 millimeters in diameter transfers a charge of 420 coulombs in 80 minutes. Silver contains 5.8 times 10 to the 28th free electrons per cubic meter. Actually, a cubic meter is an enormous volume of space for a wire, because this one's only 2.6 millimeters in diameter. But what is the current in the wire? And what is the magnitude of the drift velocity in the wire? Well, current is just dq dt, but it's supposed to be coulombs per second. And so I need to change 80 minutes into seconds. And so 80 minutes times 60 seconds per minute. Hey, that looks like 480 to me. Oh, 80 minutes, excuse me. How about 4,800? That sound better? Yeah, 3,600 seconds in an hour, and it's a bit longer than that. So oh yeah, we're 20 minutes longer than that. Okay, anyway, 4,800 seconds. So the current is going to be 420 coulombs over 4,800 seconds. And not going to be an amp, but okay, it's 8.75 times 10 to the minus 2 amperes. Okay, an ampere is a coulomb per second. So that's the current in the wire. What about the drift velocity of the electrons in the wire? Well, part B, I is equal to N Q V sub D times A. And so, oh, A is the area now. Got to be careful. This is, I'll call it area. Okay, and that's amperes. So, or coulombs per second. That might be safer. Anyway, let's go ahead and solve for the drift velocity. V sub D, and I can never remember if it's a capital D, it's a lowercase d. V sub D is going to equal 8.75 times 10 to the minus 2 coulombs per second divided by the number per unit meter or per cubic meter, 5.8 times 10 to the 28th. And this would be per cubic meter, or actually meters to the minus 3. It's just electrons per cubic meter, but the electron is just a thing. It doesn't have any units. And then let's see, what am I dividing by? Q, which is 1.60 times 10 to the minus 19th coulombs. And we're just dealing with magnitudes here. I know electrons are negative, but that's okay. And then the area, which is going to be, let's see, pi r squared. So pi times 2.6 times 10 to the minus 3 meters, and that has to be squared. Okay. That'll give me a square meter. I think I'm going to end up with meters per second. The coulombs go away. There aren't any seconds down here. I'll end up with 1 over a meter on the bottom, which will flip up top and give me a meter over a second. So meters per second, and you may be astonished at the number that we're going to get for this thing. And I hope I got all my exponents right. If we kind of estimate 10 to the 28th, 10 to the minus 19th, that'll leave me with around 10 to the 9th, maybe something like that. 9 times 10 to the 9th times pi is going to be 27 times 10 to the 9th times that. Oh, I had to square that last number. I almost forgot to do that. Anyway, I get a drift speed or drift velocity of 4, I can keep 2 sig figs, 0.4 times 10 to the minus 7th meters per second. Holy smoke. Now, if I multiply that by the number of seconds in an hour, I can figure out how far an electron on average will go in 1 hour. And on average, in this wire carrying that current, an electron travels only 1.6 millimeters, which is amazing. The average speed, that's like that far. The average speed of an electron in a wire, the drift velocity, is really slow. Holy smoke. Well, how can it be that when you flip a light switch on the wall, the lights come on almost instantly? Well, here's the thing. The wire is absolutely full of electrons. They're everywhere in there. And when you flip the switch, what travels through the switch at something, it's not the speed of light, but it's really close to the speed of light, is the electric field. That's the pressure that will push the electrons through. And that's what goes fast. An analogy that's often used for this is that if you hook up a garden hose for the first time in the spring and you hook it up to the spigot on the side of your house, you have to stand there and wait for a while, several seconds, maybe, 10 or 20 seconds if it's a really long hose. But then water will start to come out of it. If you then shut the water off, and maybe you've got a sprinkler connected to the thing, so water doesn't just drain out, then the next time you turn the water on, you'll get water coming out of that hose almost immediately because it's full of water. But before, you had to fill the hose with water, and that's why you had to wait. Well, there's no way to get the electrons out of a wire. You can't empty it of electrons. There's just too many of them. And so the instant you connect an electric field in this wire and a complete circuit, you're going to get current flow, at least for practical purposes. There would be some really short delay while the electric field races through the wire, but it's not going to be very long. And by a human time scale, it's unnoticeable. So that's what happens. Okay, now we've got an 18 gauge copper wire, which is not, you wouldn't want to use this for an appliance that uses a large amount of current, but maybe if it's some small thing like a LED or something like that, it'd be okay. But anyway, it's got a current with a current density of that 1.50 times 10 to the 6th amps per square meter. And we're given the density of free electrons in copper per cubic meter, and we want to calculate the current in the wire and the drift velocity of the electrons. Well, current density, J, is equal to the current divided by the area. So we know what the current density is. We know we'll have to calculate the area, but the area is just going to equal pi r squared for this thing. So it'll just be pi times 1.02 times 10 to the minus 3 meters squared. That's not bad. Pretty small area, 3.27 times 10 to the minus 6th meters squared. So the current will just equal A times J. So that area, 3.27 times 10 to the minus 6th square meters times 1.50 times 10 to the 6th amps per square meter. 10 to the 6th, 10 to the minus 6. Looks like we're going to have around 5, but we'll find out. .90 amps. Yeah, just plain old amps, coulombs per second. Okay, now the drift velocity or the current is actually equal to NQ V sub D times A. Well, it's actually easier in this case, instead of having to plug in the A again. If we're after the drift velocity, V sub D will equal I over NQ A. And the I over A is just J, so this is just the current density divided by N times Q. And that way I punch in one less number, I guess. So I'll take that current density that they gave me, 1.50 times 10 to the 6th. This is amps per meter squared, but it's actually a coulomb per second meter squared, because an amp is a coulomb per second. And then on the bottom, I'll have that number of free electrons per cubic meter, 8.5 times 10 to the 28th. We're going to be down to 2 sig figs now. And that's electrons per cubic meter, but it's just like meters to the minus 3 on the bottom. You can think of that as being a per cubic meter. And then the charge on the thing, on the electrons, is 1.6 times 10 to the minus 19th coulombs. Okay, so we've got a coulomb on top, which will divide with a coulomb on the bottom. These meters to the minus 3, you can take them up and they'll become meters to the plus 3. And meters cubed over meters squared is just meters, and so we'll have meters per second, a drift velocity. Now, this might be a more believable, although it's a pretty large current for only an 18 gauge copper wire, that's going to get kind of warm, I think. But And you might, that'd be a fire hazard, I think, actually carrying that much current on a skinny wire like that. But this is a more believable or more realistic situation because you typically don't have silver wire like the previous problem. And that's kind of pricey. Copper wire is more common, although it's getting pricey too. Anyway, 1.5 equals 6 divided by that. And this time I get quite a higher number, 1.1 times 10 to the minus fourth meters per second. And if I multiply that by 3,600 seconds, so V sub D times 3,600 seconds, this will tell me how far those things go in an hour on average. Oh yeah, these things are real hot rods. I would get, see, about 40 centimeters. That's what I get. So in an hour, well, that's 30 centimeters there. So you'd have 10 centimeters farther than this. So, but still, that's for an hour, how far an electron would go on average. And they just don't go that fast. They don't have to be, I guess. Okay, let's try something else. Oh, now we're going to look at the magnetic force on a moving current. And let me show you how that comes about. I'm going to imagine that you have a wire here that's carrying a current. And so it's going to be full of electrons in here. And on average, they're moving in that direction with a drift velocity, V sub D. And then we'll take an external magnetic field. So let's have the current going in that direction. Let's imagine that the magnetic field is pointing down here, and it's a uniform magnetic field. So that's B in that direction. And if we were to look down the wire and get a different view of this. So now we're looking down the wire's into the page. The drift velocities are all into the page, so I'm going to mark them as little X's here because they're a vector that's pointing away from us. And we've got this magnetic field that's pointing down here. Okay. Well, on each one of those little electrons moving in that direction with a velocity V sub D, and again, it is just an average. Some are going faster, some are slower, but on average, that's what's going on. On each of those moving charged particles, you will have a force on it. F equals QV cross B. Now, I've talked about this a little bit, but with the cross product, in this case, I'll have the magnetic field that's perpendicular to the drift velocity. When you have a cross product, point your fingers in the direction of the first vector, the velocity, which in this case it'd be into the page. So this is kind of hard to illustrate, but into the page, and curl them in the direction of the second vector, cross the B, and the V cross B B is in that direction, and the force will be in this direction. Well, what that means is the V cross B is going to point this way, but electrons have a negative charge. You'll actually end up with QV cross B points in that direction. But that's only the force on a single moving electron. Okay, how are we going to deal with a whole bunch of electrons doing this? Well, let's imagine a little length of wire that we'll call DL. And maybe I'll use a capital L for this. Okay. And in that length DL, how many electrons are there going to be in there? Well, the wire has a cross-sectional area A. ADL would be the volume of that little thing here. Oh, and my DL is going to point in the direction of the current flow. It's a vector. So DL is going to point that way. Well, the volume in there is of this little chunk here is going to equal ADL. Okay. How many electrons are in there? Well, there's N electrons per unit volume, and so the number of electrons in that volume will equal NADL. And on each one of those electrons, there's going to be a force QV cross B. And so the total force on that little chunk DL will equal, I take the force on one electron and multiply it by the number of electrons that happen to be in there, and I'll get, let's see, F net is going to equal Q V, whoops, this is V sub D cross with B times N A DL, and actually I want this to just be a number. I'll kind of change this around a little bit. I'll have N A Q V sub D. Oh, let's see. Or this could be the magnitude. Yeah, that's what I want to do. I want to have DL pointing in the same direction as the drift velocity. But at any rate, this NAQV sub D or NQAV sub D, this is the current. And what you end up with for the net force, if we define a vector DL to be a vector that points in the same direction as that, the force that's on that little chunk of stuff here is equal to the current times DL cross B. And this is the force on a section of current in a uniform magnetic field. If you've got a non-uniform field, you have to go to all sorts of work to, well, you'd integrate over the entire thing, but we'll stick with uniform fields just for simplicity. So that's the force on a chunk of current. All right. Now, On this thing, we've got a horizontal rod with mass M and length L aligned in a north-south direction. The rod carries a current I in the direction toward the north. So now we imagine that we've got this rod that's got current going through it. And this is north up here, and this is south. So there's a current I in the wire. When a uniform magnetic field B is applied to the entire length of the rod, the magnetic force on the rod keeps it suspended at rest in midair. I think we're going to need to take a new viewpoint. So now let's suppose that we've got wires hanging down connected to this rod here. It's hanging from the wires, and it says the current's going in the direction toward the north. So the current would come down this wire, go through the rod, and then go back up this wire here. And we're just interested in the force on the rod. Okay, so IDL would point in this direction. And in order to have IDL cross B pointing up, having the magnetic force on the rod keep it suspended at rest. Okay, this is the right-hand rule again. I have to imagine DL goes that way. The force goes that way. My B would have to be into the page in this case. So I'm going to have a uniform magnetic field that points horizontally in order to get a vertical force out of this thing. So this is B into the page. And that way you'll have a magnetic force on this thing that's up. And here, even though we know that it's electrons that are the charge carriers, when we talk about an electric current, we pretend it's positive charges going that direction. We actually know it's negative charges going this way, but it's just customary to assume that the current flow is somehow positive charges going in one direction. So that's a bothersome thing. All right, well, what's the minimum magnitude that B can have? Well, this rod is going to have a weight, mg, and so you have to have that, the magnetic force on this thing. Yeah, this is B into the page. This is IDL. Actually, this thing has a length L, so this would be ILB. The minimum force upward is when L and B are perpendicular to each other. So it's actually, you can think of it as the magnitude of IL cross B is what that net force happens to be. And if you've got a straight segment in a uniform magnetic field, that's what the IDL cross B turns into. Okay, so upward force of ILB equal in magnitude to the weight of this thing. So ILB has to equal mg in magnitude. And so the magnetic field, the minimum strength that we'll have is going to be mg divided by I times L. And that's all we can do. Oh, and then find the direction of B if it has the magnitude found in A. Well, it's going to have to be into the page. So if you're looking down the rod, so the current is going in this direction, and that's what an X indicates. The magnetic field is going to have to point in this direction. That's supposed to be horizontally B, and then IDL cross B is going to be this, or IL cross B for the entire length of the thing. That's going to be up, and mg is down. then those two would be balanced. Okay, kind of a weird problem. Okay, here's another one. Similar to this. Here you have a thin 50 centimeter long metal bar. That would be that thing here. With a mass of 0.750 kilogram, rests on but is not attached to two metallic supports in a uniform 0.450 Tesla magnetic field. This doesn't show up well on here. If you print it off for yourself, you might see it a little better, but there's little X's here going into the page, and that represents this magnetic field. And a battery and a 25.0 ohm resistor in series are connected up here to the supports. What is the largest voltage the battery can have without breaking the circuit at the supports? What in the world is going on with that? Well, did they give us, oh, this is 25 ohms here. And that's the only resistance in the circuit, because this metal bar is like a really fat wire, kind of. Okay, so how are we supposed to figure this out? Well, this bar has a length that'll be in this uniform magnetic field, and if the current is going in this direction, IL cross B, if the current is too large, the magnetic force would lift this thing off of these metal supports and break the circuit. So what we would have to have in that case is ILB equaling mg, and I, the current in the circuit, this is an Ohm's law problem, that the voltage drop across this 25 ohm resistor is going to equal the voltage of the battery. And so we can say that V equals I times R, or E is the way that you write the potential difference of the battery. And we don't know that. Okay. So I is equal to E divided by that resistance there. And R equals 25.0 ohms. So there's the current. We've got this stuff here. Let's see. We know the strength of the magnetic field. We know the length of the rod. We know the mass of the rod. So that current will equal E over the resistance of that thing times L times B will equal mg. And we're actually just solving this for L. If you have the voltage at this value, it'll just balance the magnetic force, which is going to be upward. The IL cross B is going to be upward. It'll just balance the weight. But if you make it any more, then this magnetic force exceeds the weight of the rod and you break the circuit. So we just have to solve for this. And let's see if we get the right units. The EMF of a battery, or the battery voltage, they call it, has units of volts. And so somehow when we do all this stuff, we should end up with units of volts. So let's see how that happens. We'll have M times G times R. So this is going to be a Newton times an ohm. Good grief. All kinds of weird stuff going on here. Divided by LB. Let's see what happens with this. Okay. The mass of that thing is equal to 0.750 kilograms. G, of course, that one I don't have to look up. 9.81 meters per second squared. R is the resistance of that thing. 25.0. Now, with V equaling IR, R is V over I, and then the resistance is in ohms, but an ohm is going to equal a volt per amp. So, yeah, volt per amp. And we'll have to see what comes out of all this stuff. Okay, L has a length of, it's 50 centimeters. That's 0.500 meters. So we've got that. And B, the magnetic field strength, it's 0.450 Tesla, but a Tesla is a Newton per amp meter. Whew. This is all kinds of weird stuff. Well, let's see, a kilogram meter per second squared is a Newton. So I can cross those out, and I've got that there. Then I've got a meter here and a meter there. Those divide out. And so I've got 1 over an amp on the bottom. When I invert that and multiply, I'll have an amp over 1 here. And those will divide out, and I'm left with volts. Whoosh. These problems are getting really complicated on the units. And that's why that table that you had with the test yesterday, keep that thing and or print it off. I think I've given you access to it before. So anyway, 0.750 times okay, and then they have to make it complicated. Okay, times 25 divided by okay, sig figs, 3 on everything. Looks to me like 818 V for volts. So that's a pretty big battery, actually, especially with only 25 ohms here. And then it says, if the resistor suddenly gets partially short-circuited, decreasing its resistance to 2.0 ohms, find the initial acceleration of the bar. Okay, well, that would be exciting. Especially with a battery that big and only a 2 ohm resistor in the circuit. If the bar didn't jump off, this would probably start to smoke, I think. All right, well, we're going to have another piece of scratch paper to be able to do this. So first thing I'll do is figure out the current in the circuit that we have there with an 818 volt battery. So we've got this thing. I think that's the way they had it connected in the circuit. Yes, it is. So plus and minus here. And now we've only got a 2 ohm resistor in there. And 818 volt battery. We come down here and let's see, we've got those supports. We have the bar that's sitting on the supports. And this is just a nice conductor down here, but it won't be for long. So V equals I times R. This would be like the voltage drop across this resistor. But we know that the voltage drop across the resistor is the same as this thing. If you redrew the circuit measuring across here, you could take this other lead and bring it all the way over to here, and you'd be measuring the potential difference across the resistor, and it's the 818 volts. So the current in this case is 818 volts. We don't need a calculator for this, over 2.0 ohms. And that looks to me like 409 amps. That's a ton of current. I don't know what kind of wires they've got in this circuit, but they wouldn't last long if they weren't really heavy. So anyway, there's that. Now, in this case, we know the upward magnetic force. It's going to equal ILB. Okay, remember the magnetic field was into the board, into the page here. The current's going that way. And as a vector, that upward force would equal IL cross B. But the magnitude is, in this case, is going to be ILB. The cross product has a sign of the angle between the current and the magnetic field, which is 90 degrees in this case. And so sine of 90 degrees is 1. So the force, magnetic force, is just ILB. All right, so that'll be the upward force. The downward force is mg, and so you'll have ILB upward and mg downward. So the net force, sum of the forces, is going to be ILB minus mg. We can plug this in, 409 amps. We're going to be out of time after this one, times L, which was 0.500 meters. These are pretty varied problems. And so read the book, do some of the simple examples, come back and revisit these problems on your own. And then the 0.450 Teslas minus 0.750 kilograms times 9.81 meters per second squared. Whoosh. All right, so the net upward force is going to equal 409 is altogether 92.0 newtons minus that minus 7.36 newtons. So the net upward force is should be able to do that in my head. It's 84.6 newtons. And that'll equal MA for an instant. The instant that thing comes off the supports here, the current's broken and the magnetic force is going to vanish. So it'll just jump and for an instant. But anyway, the acceleration is 84.6 newtons divided by 0.750 kilograms. And okay. I guess I've got 3 sig figs. 113 meters per second squared, but only for an instant. And so it's not going to have much time to acquire any speed. Okay, that was quite a varied batch of problems here. I don't know if I had another one in here. Yeah, have to look at that another time. But at any rate, I'll stop the recording here.